Hey everyone, and welcome to The Explainer. I'm really thrilled you're here because today we're going to completely unpack Chapter 7 to reveal the invisible math that basically governs our entire visual and physical world. We are diving deep into the fascinating mechanics of proportional reasoning. Have you ever looked at something and just wondered why it looks naturally right to your eye, while other things just look incredibly off? Well, it's not magic, it's math. And by the time we wrap up today, you're going to have a completely new lens for seeing pretty much everything around you. Okay, to kick things off, I want you to rely purely on your intuition for a second. Look closely at these two tigers. The one on the left, that looks like a perfectly normal, majestic animal walking through the grass. But the one on the right, it looks completely ridiculous, right? It's squished, it's kind of artificially fatter, and your brain instantly throws up this massive red flag saying, whoa, something is definitely wrong with this picture. But what exactly is triggering that alarm in our brains?
Well, to figure it out, we actually need to look at the numbers. Now, we already know this intuitively, but check out the actual data. Image A, our normal tiger, has a width of 60 millimeters and a height of 40. Now, image E, our weird squish tiger, has a width of 60 and a height of 60. It literally became a perfect square. But if you look at image C, the width is cut exactly in half, down from 60 to 30. And the height is also cut exactly in half, from 40 to 20. Because both of those dimensions change by the exact same mathematical factor, multiplied by 1/2, the image looks identical to the original, just smaller. So our brains naturally detect when width and height change by different factors.
So it really all boils down to this core question: why do some resized images look perfectly normal while others look completely ridiculous? The short answer is that your eyes are basically performing complex algebraic comparisons constantly, without you even realizing it. When the numbers align, the world looks right. When they don't, well, we get a squishy tiger. Today, we're taking that intuitive visual logic and translating it directly into the formalized mathematics of Chapter 7.
Okay, let's dive into this. Here is our roadmap for today. 1. Spotting similarity and change. 2. Understanding ratios and proportions. 3. The rule of 3. 4. Sharing but not equally. And 5. Proportions in the real world.
All right, kicking things off with Section 1, Spotting Similarity and Change.
Moving right along to Section 2, Understanding Ratios and Proportions.
So like we just saw with those tiger photos, the images that looked perfectly normal to us all shared a hidden link. Their widths and heights changed by the exact same multiplying factor. That visual similarity is entirely governed by specific mathematical relationships. And the very first tool we need to understand those relationships is the ratio. Simply put, a ratio is a way of comparing two quantities. It represents a proportional relationship, usually written as A:B. This just means for every A units of the first thing, there are exactly B units of the second thing. Think back to our original normal tiger. It had a width of 60 and a height of 40. Its ratio of width to height is 60 to 40. That specific relationship mathematically locks in the shape, keeping it looking completely natural.
But here's what's actually super interesting about this. You can have totally different sets of numbers that actually represent the exact same proportion as long as you reduce them to their simplest form. Look at ratio 1 from our small image, 60 to 40. If we find the highest common factor, which is 20, and divide both numbers by it, we get 3 to 2. Now look at ratio 2, which comes from a much larger image, 90 to 60. The highest common factor there is 30. Divide both by 30, and boom, you also get 3 to 2. So even though the overall sizes are completely different, their simplest form is exactly the same. And that is exactly why the tiger looks perfectly normal in both versions.
And that brings us to the core definition of a proportion. A proportion is literally just when two ratios are identical in their simplest form. To show this mathematically, we use a double colon symbol. So we'd write 60 is to 40 as 90 is to 60. Setting two ratios equal to each other like this is incredibly powerful. It's the absolute foundation for solving complex mathematical problems. Why? Because, and this is the real secret here, if you know 3 of those numbers, you can absolutely always find the 4th. Which leads us perfectly into Section 3, the rule of 3.
Finding that 4th missing piece of information is exactly what this rule is all about. In ancient Indian mathematics, this formalized strategy was actually known as trirashika. It's essentially the magic key that unlocks missing data in almost any scenario. Let's look at how methodically this works. Imagine a car travels 150 kilometers in 90 minutes. How far will it travel in 4 hours? Step 1 is to model the proportion. But actually, wait, You can't compare minutes to hours. Consistency is absolutely crucial here. We have to convert the 4 hours into 240 minutes first. So our model becomes 150 kilometers is to 90 minutes as x kilometers is to 240 minutes. Step 2, we use cross-multiplication. We multiply 150 times x and set it equal to 240 times 90. In step 3, we simply solve for x, which gives us 144 kilometers. Treyer or Shika strikes again.
All right, on to section 4, sharing but not equally.
So what if you're not looking for a missing number, but instead you need to split up a total quantity of something? And what if you don't want to split it just straight down the middle, 50-50? We do this all the time, right? We're mixing ingredients, making paint, dividing up money based on who invested what. To divide a total quantity into a specific ratio, let's call it m to n, we follow a really simple 3-step procedure. Step 1, figure out the total number of parts by adding m and n together. That gives you your total number of groups. Step 2, divide your entire quantity by that number of groups. That tells you exactly how big just one single group is. Finally, step 3, multiply that single group size by your original m ratio number and then by your n ratio number to see exactly how much goes into each separate pile.
Let's see this in action with a chemistry lab example from the source material. Say we need to create a 240 milliliter solution mixed in a ratio of 1 part acid to 5 parts water. First, we add those ratio parts together. 1 plus 5 equals 6 total parts. Next, we divide our total volume, which is 240 ml, by 6. That gives us 40 ml per single part. Finally, we just multiply. The acid gets 1 part, so 1 times 40 is 40 ml. The water gets 5 parts, so 5 times 40 is 200 ml. If you add 240 back together, you are right back at your perfect 240 milliliter solution. It works every single time.
And that brings us to our final stop, section 5, proportions in the real world. Because look, proportional reasoning isn't just about tigers in a digital photo or, mixing acid in a beaker. This exact same foundational math scales infinitely. The rules literally do not change based on size. Whether you're mixing a cup of juice, calculating the mass of a huge gold block, building a house, or literally exploring the cosmos, the rule of 3 holds it all together.
Take this massive number, for example, 15,660. The text outlines this great scenario where a mason is building a house. They know that to build just a 10-foot wall, it takes exactly 1,450 bricks. They measure out all their blueprints and realize the total length of the walls they need to build is 108 feet. Using the exact same ratio modeling we just learned, 10 is to 1450 as 108 is to x, they can perfectly calculate that they need to order exactly 15,660 bricks for the job. No guesswork, just pure, solid math.
Or let's go even bigger. Planetary scale. The Earth travels roughly 940 million kilometers in its orbit around the Sun over the course of a 52-week year. Imagine I asked you to calculate exactly how far we are hurtling through space in just one single week. Guessing would be pretty tough, right? But setting up a proportion, 940 million is to 52 weeks as x is to 1 week. You just solve it, and boom, exactly 18,076,923 kilometers per week. We just calculated planetary orbital distances using the absolute exact same formula we used to figure out how much water to put in a lab beaker. That is the immense universal power of setting up a simple x to 52 proportion.
So I'm going to leave you with this thought. If a simple ratio can fix a distorted, squished photo of a tiger, perfectly portion out a scientific chemical mixture, construct a massive building without wasting materials, and even calculate planetary orbits, what other invisible proportions are shaping your daily life? Look around you today. Try to spot the Triozakasica, the rule of 3, out in the wild. I guarantee you'll be amazed at what you find now that you know exactly what to look for. Thanks for hanging out with me for this explainer. Keep asking those big questions, and I'll catch you on the next one.